Hi there everyone. Your choice of prop is probably one of the most important component choices that you make when you're building your drone. The prop has more of an effect on thrust, power, prop wash handling, and top speed than almost any other component that you're going to pick on the drone. And not only that, it's also one of the cheapest and easiest components to change to get very, very different flight performance. In this video, I'm going to test over 20 different props and give you the lowdown on which are the best for freestyle, the best for racing, and which are ones that I suggest you avoid. So let's not waste any more time and let's get right into it. So before we look at the results of my testing, I want to take you through the test setup that I've used to collect this data. This is the Taito Robotics 1585 thrust stand, and I think it's the ideal tool for testing these 5-inch props. It collects so much data at once that you can just do one test on this piece of equipment and have everything you need to know about the performance of the prop and motor. The prop I've got set up in a pusher configuration, so the air is being pushed out this way. And I've tested it both ways round, and I get much higher thrust numbers and efficiency numbers running the prop this way round. And I think it's because there's just too much material behind the prop blocking the thrust column to get the best performance running it the other way around. The motor that I'm using is the iFlight Zing 2 1855 kV. And you can see that I've put a piece of white tape on it here. And this white tape is for the optical RPM sensor. So as the motor is spinning, this white tape is passing an optical sensor. And every time it passes the sensor counts it. And that way it can very, very accurately determine the RPM of the motor. And because a prop is fundamentally dependent only on RPM for the thrust that it produces, you need to get an accurate measure of RPM to understand the performance of the prop. Moving backwards, we've got these two load cells here. These two load cells, and one back here as well, I don't know if you can see that. These two load cells measure the torque that the motor is applying to the prop, so we can see how the prop responds to torque. And up on the top here, I have the ESC and control board that drive the motor. And I'm using the Diatone Mamba F50 Pro 128K ESC to drive this motor. And I'm using my BL Heli 32 recommended settings. So that's 24K to by RPM for the PWM frequency, 16-degree timing, and 50% ramp-up power. At the back here we have another electronics board, and that's measuring the voltage applied to the motor and also the current that's being drawn from the motor as well. It also has an accelerometer on this board, so it can measure the vibration associated with this whole system, and that's really handy because if the prop is slightly out of balance, you'll get a lot more vibration of the test stand, and you can measure that with the accelerometer on this board. All of this data is being logged at about 100 times a second for this testing, so we get lots and lots of data points to compare these props to each other. The whole system is being powered by this 5200 milliamp hour pack, and that's being kept topped up by this benchtop power supply so that the voltage is always constant at 24 volts. When it comes to actually running the test, I'm using the automatic control feature of the GUI software that comes with the thrust stand, and I'm running the same script every time. And that's just ramping the ESC power from 5.5%, which is the typical idle value for a quad, up to 100%, and that test is the same for every prop that I tested. So it's time for me to show you what a test looks and sounds like. And for this, I'm going to need eye protection and ear protection. So let me put these on and then we'll run a test. Alright, so now you know how I got the data, let's take a look at the results. And I was pretty surprised, and I think you're going to be too. Let's start by talking about weight. And weight is a really important measurement because it's very closely correlated to the moment of inertia of the prop. And a prop with a larger moment of inertia is going to be harder for a motor to spin up or slow down. And the result is that the quad is going to be less responsive. The faster that the motor can spin up and slow down the prop, the quicker the quad is going to be able to respond in things like prop wash, and the more stable and smooth it's going to be in the air. The lightest prop that I tested was this HQ 5.1 by 2.5 by 3, very light pitch prop. And the heaviest prop that I tested was this HQ R42, which is a prop designed for racing. In general, the steeper pitch props tended to weigh more. I think steeper pitched props need to be heavier because they need more material in the prop blade to keep it stiff under the high aerodynamic loads that they face compared to a lighter pitched prop blade. Manufacturers don't want a steep pitch prop flattening out at high RPMs and losing the benefit of that pitch, so they add a bit more material to keep those blades a little bit stiffer. But the result is that the prop ends up a little heavier overall. The next thing I want to talk about is efficiency. And before I jump into the table of values, I want to talk about the shape of the efficiency curves for all of these props. So on the y-axis we have the power that they consumed, and on the x-axis the thrust that they delivered. So anything that's sort of over here is very efficient because it's producing a lot of thrust for very little power, and anything up here is very inefficient because it's producing not very much thrust and it's consuming a lot of power. And the thing that I want to call your attention to is the fact that these curves don't really cross over each other as we move up in thrust. So a prop that's very inefficient at low thrust is also very inefficient at high thrust. And a prop that's very efficient at low thrust remains very efficient all the way up to high thrust. So if we're looking to compare the efficiency of different props, we can pick a point, for example, 1 kilo of thrust here, and look at the efficiency of the props at that point, and that will give us a good comparison of the overall efficiency of the props across their entire thrust range. So that's what we're going to look at now. This is the efficiency of all of the props at 1,000 grams of thrust. That's a good measure. All of the props were able to achieve 1,000 grams of thrust, but they all used very different amounts of powers to do it. You can see that the most efficient prop is this HQ 5.1 by 2.5 by 3 again. So that's coming out top with an efficiency of 2.64 grams per watt. And the 3D prop, the HQ 3D 5 by 3.5 by 3, is the least efficient by quite a margin. And I think this goes to show that when you're trying to make a 3D prop, so a prop that you can run in either direction and produce thrust in either direction, you really take a hit on the efficiency that's really significant. What I find particularly interesting looking at this chart of efficiency is that there doesn't seem to be much correlation between the pitch of the prop and its efficiency. You can see that we have some props that are very steep pitch, like this Dal Spitfire, that's still efficient, and we have some props that have a very low pitch, like this Dal Cyclone and the J40, but they're still inefficient props. This goes to show that I think you need to test these props on a thrust stand to understand their efficiency. Alright, now we get on to max thrust. And this is like the bench press or deadlift of prop testing, right? It's just what's the biggest number that these props can put up. And what we find is that the prop that actually delivers the most thrust in my testing is this 5.1 by 3.6 by 3 prop from HQ. And it puts up over 1,600 grams on this iFlight Zing 2 1855 kV motor. And down at the bottom, we again have this 3D prop, bottom of the charts. It doesn't produce much thrust. It's not very efficient. Obviously, you're compromising its performance because you want it to be able to produce thrust in both directions. Other good performers are this Nazgul F5 that produces plenty of thrust, as well as these V1S props by HQ, the 4.8 and the 4.5 also put up good thrust numbers. Once again, it's not as simple as a steeper pitched prop is going to deliver more static thrust than a lighter pitched prop. We can see here that the two top performers have a relatively modest pitch, 3.6 and 3.5. I think this goes to show again why thrust stand testing of props is so important. You wouldn't know what thrust the props are able to produce just based on their diameter and their pitch. There are 5-inch props that produce huge amounts of thrust. There are 5.1-inch props that produce, relatively little, like this Dal Cyclone down here. And you have steep pitch props that produce a lot of thrust, but also shallow pitch props that produce a lot of thrust. So it's quite difficult to predict the performance of the prop based purely on its diameter and pitch. Really, you need to test the prop on a thrust stand to know how much static thrust it's capable of producing. A static thrust test alone doesn't tell us everything we need to know about how a prop is going to perform in the air. Props have this phenomenon where they deload as the quad accelerates. That means that the amount of thrust that the prop produces at a given RPM reduces the faster the quad is flying through the air. Now, there is a parameter which captures that behavior, and it's called the advance ratio. And the advance ratio of a prop is the ratio of the free stream fluid speed to the propeller tip speed. And a larger advance ratio predicts a higher top speed, all else equal. So a larger advance ratio for a given amount of thrust predicts a higher top speed. Now, how can we calculate advance ratio for a static thrust test where the free stream fluid speed would be expected to be 0? Well, one way we can do it is by looking at the speed of the air moving through the propeller disc. And we can calculate the speed of that air by looking at the thrust that the propeller produces. So if we take a momentum balance of the prop, we have the prop producing a certain amount of thrust, F, for a certain amount of time, T, and to produce that much thrust, it has to change the momentum of a certain amount of air. So this is this delta mv here. Now, the mass of the air that it's changing, we can calculate as a cylinder with a length that is the velocity of the air that's moving through and a radius that's the radius of the prop. So every second, this cylinder of air is moving past the prop. The mass of that cylinder of air can be found by taking its volume, pi r squared v, multiplied by the density of air rho. And then the change in momentum, we can assume that all of this air starts off at 0 speed, because this is a static thrust test, and it ends at the speed v, the velocity of the air moving through the prop. So then we end up with the thrust being able to be calculated by looking at the density of the air multiplied by the area of the prop disc multiplied by the velocity of air moving through the prop squared. And that allows us to calculate this proxy for free stream fluid speed, V. Now, it's not true free stream fluid speed, but if we use that proxy value, we can calculate a sort of advance ratio for a static test. Now, if we look at this advance ratio for all the different props, we can say that a prop with a larger advance ratio, so a prop sitting at the top of this list, is going to deload less as you accelerate through the air, as your quad accelerates, and therefore is probably going to be able to achieve a higher top speed than a prop with a very low advance ratio. Now, thrust does play into this a little bit, as does prop diameter, as does prop pitch. But what we can see is that the Ethics S5 came out with the largest advance ratio. So this is the prop that I would predict would have a very good top speed for your quad. Whereas if we look down at the bottom, the Dow Cyclone has a much lower advance ratio. It's about 25% less. And so we can see that that prop is going to have a lower top speed. It's going to deload much more quickly as the quad accelerates, and the amount of thrust it's going to be able to produce falls off a lot. What we can see is that the Ethics S5, the Nazgul F5, and the Emax Avon Flow all have really high advance ratios, as does the R42, which is what we would expect for a racing prop where you're wanting to be able to achieve a high top speed with your racing quad. So for racing quads, you're definitely going to be wanting to look at the top of this list to find a prop with a nice high advance ratio so that you can get up to a nice high top speed on the straights. If you're looking for freestyle performance, advance ratio may be a little less important to you. You may not care about the maximum top speed that your quad can achieve, and therefore you may not mind picking a prop with a lower advance ratio that has other properties that are beneficial for freestyle, like a very light weight or a low pitch that's going to be resistant to prop wash. So up here for racing, and probably a little lower, maybe down here for sort of freestyle, low speed type applications. The final property I want to talk about is vibration. And vibration is an important parameter for me because props create a lot of vibration, and the more vibration they create, the more they affect your ability to tune your quad. So the more vibration your quad has, the more filtering you're going to need to apply, which increases delay on the PID loop, and you're not going to be able to push your D gains up as high without getting hot motors. And that's going to affect the responsiveness to the quad and prop wash handling and things like that. So having a prop with low vibration means that the prop has been really well balanced out of the factory, and so as it's spinning, it's not generating much vibration at all. You can see here up at the top we have some really good performers, and they're producing less than half a G of vibration at 20,000 RPM. And then the worst performers are producing a little bit more vibration, and some, like this Dow Spitfire and the Azure Power, are producing really quite a lot of vibration, getting up for 1G or even more than 1. So that's going to affect your ability to tune the quad, because twice the vibration from the prop is another 3 dB of noise on the gyro that you're going to need to filter out. So just worth bearing in mind, props with low vibration are going to help with tuning. Now it's time for the conclusions. But before we find out which prop is best for freestyle and which prop is best for racing based on this testing, it's time for a sponsor slot. And that sponsor is you guys, because I haven't got a sponsor slot for this video. I didn't get any sponsorship to make this video. I bought all the props myself. So if you would like to support the work that I'm doing, I'd really appreciate it if you check out my Patreon. You can join for just a few dollars a month, and it'll give you sneak peeks of all the work that I'm doing, and also help me make more videos like this to support all of us in the community of FPV. So I'd really appreciate it if you check that out. But now, time for the conclusions. To be objective about the conclusions, I've given each of the props a ranking on each of the parameters. So for weight, I've given the number 1 rank to the lightest prop. For efficiency, I've given the number 1 rank to the most efficient prop. For thrust, I've given the number 1 rank to the prop that produced the most thrust. And for advance ratio, I've given a rank for the prop with the largest advance ratio. That gets ranked number 1. And for vibration, the prop that produced the least vibration gets the number 1 rank. And then to calculate a total for the ranks, I've just taken the average rank that the prop gets across all parameters. Now for this table, I've not included the advance ratio in the ranking, because you don't necessarily want a prop with a large advance ratio. Sometimes a prop with a smaller advance ratio is actually going to be better for things like freestyle. So for freestyle, I think that the best prop in my testing was the HQ 5.1 by 2.5 by 3, because overall it was the lightest, it had the best efficiency, it was middle of the road in terms of thrust, and it had one of the best vibration numbers. So overall it gets a rank of 4.3. The worst prop for freestyle is the HQ 3D prop. And, we talked about it before, you do compromise performance to have that ability to run the prop in both directions and get thrust in either direction. So to make it symmetric in that way, you do sacrifice some performance. But you can see the list here of all of the props and how they perform on each of the ranks. So you can always pause the video and have a look at the prop that you're interested in and see how it compares to the others on any of the parameters. If we now look at the ranking with advance ratio included, and we say that actually we do care about having a prop with a large advance ratio because top speed is important to us, for example for racing or just for flying faster, then we can see that that does change the order quite a bit, and the Nazgul F5 comes out as the best performer across all of the different parameters with an average rank of 5.2. And the HQ DP V1S prop, 4.3 inch pitch, also comes out really well. And we see that the 5.1 by 2.5 by 3 still comes out pretty well, but obviously it's got a very poor ranking in terms of advance ratio because it's got that very shallow pitch, and so it drops down the order a little bit. Obviously, if you weight the factors differently, this is just an average weighting, but if you weight advance ratio really highly, then you can go and look at something like the Ethics S5, which has the best advanced ratio. And if you really care about maximum thrust, you can go and look at something like this 5.1 by 3.6 by 3, which gets the best thrust rating. So it's really up to you how you use this data to choose which prop is right for you. So there we have it. I'm definitely going to be trying out these 5.1 by 2.5 by 3 props from HQ on my freestyle quad, because I was really impressed with how well they performed, and honestly, I don't really care about top speed for my freestyle flying. And these iFlight Nazgul F5 props, a great all-rounder it would seem, so good for anything, freestyle racing. Let me know down in the comments what you think of the data. There's going to be links down in the video description to a spreadsheet with all this information so you can sort it, look through it at your leisure, take your time and figure out what prop is going to be right for what you want to do. I hope you've enjoyed the video. If you have, hit the like button. If you want to see more, subscribe. And if you want to go the extra mile and support more work like this, there's always Patreon. That's all I have for you for today. So until next time, I wish you all very, very happy flying. And I'm interested to see what you say down in the comments.